Alright, the last sort of big rule for derivatives. Alright, so the derivative of the exponential we've done, and now the derivative of the logarithm, but we're only going to look at the logarithm base e, which is again called the natural log, because it occurs in nature, and it's the one that we can always convert to. Alright, so it's the natural log. You can find derivatives of other logs, log base 10, log base 2, but those are actually more difficult, and we don't do them in this class. We only look at the natural log because it's the easiest derivative, and it's the one that occurs most often in applications. We can always convert to it. Alright, so remember, the natural log is the natural log is a log function. The ln of x just represents log base e. Right? It satisfies the function e to the y equals x. All right, that's what the function equals. It equals what exponent on my e, base e function, will give me that x value inside the logarithm. All right, so remember, that's what the natural log is. All right, so the derivative. All right, and the domain, and we're going to get a little bit more into, again, understanding that the domain is always positive. If you try to take, there's a natural log key on your calculator. If you try to take the natural log of a 0 or any negative value to give you error, because it doesn't exist. You can only plug positive values in, because if you take e to the y equals that x value, you can only get, the x can only be positive, right? E to the y, and it doesn't matter what y is, this will always be a positive number. All right, so it's kind of like the square root function, right? I can only have positive values in the square root function. This one's even more strict. I can only have positive values and not 0, right? Positive and non-zero values. All right, so the ln, natural log of x, the derivative of the natural log of x, again, it is a simple derivative. And what's nice about the derivative is it no longer has a natural log in it. Look at, so if I have the ln of x, its derivative is 1 over x if x is greater than 0. Another way that we can do this is sometimes, because instead of writing that, we'll take the derivative of the natural log of the absolute value of x and write 1 over the absolute value x. X just can't be 0 in that case. This allows us to look at positives and negatives, but the derivative function, just like the original function, can only have positive values. 1 over x is the derivative of the natural log function for the 1 over x piece where the x values are positive. All right. Now the chain rule. So just like the exponential function's derivative was pretty simple when it was just the exponential function, the natural log function is pretty simple when it's just the natural log. All right. 1 over, you have to remember, 1 over x. The chain rule is where you have to pay a little more attention, right? The natural log of x, if there's something other than x inside, or other than just the single variable inside, it can be as simple as a negative x, or a 2 times x, or a 10 times x, right? Or more complex, x squared plus 4 inside, more complex inside. But the idea is there's a function of x inside that's differentiable, all right? And so we've got an inside part, since there's something other than just x in there. And when we take the derivative, it's the chain rule. The chain rule for the natural log, the derivative of the natural log is 1 over what's inside, right? So when it's just x, 1 over what's inside is x. Well, when it's something other than x, it's still 1 over what's inside. What's inside is just a little more complicated, but it's still 1 over that expression, just like the 1 over x. But you have to remember the chain rule. There's always a second part to the chain rule. I have to then remember to separately, separated by a multiplication, multiply by the derivative of what's inside. And so you get 1 over whatever's inside the natural log times the derivative of what that expression was inside, so whatever that g of x represented. Notice again, there's no natural log at all. So when we take a derivative of a natural log, its derivative no longer has a natural log in it. When it's just strictly a natural log. And so what we get is we get this ratio. The bottom function's the inside function, the top function and the fractions, the derivative of the inside. All right, and again, that's helpful because eventually we are going to get to a place where we're going to go backwards. Start with a derivative and work backwards. And so this is an important ratio to sort of remember. Just to do a simple example before we get into the more complex example. Suppose I have the natural log of 10 times x cubed. All right, so 10 times x cubed. So again, the g of x part would be the 10x cubed. That's the inside. The outside is the ln part. Right, so when we take the derivative of this, the derivative of the natural log is 1 over what's inside. So 1 over 10x cubed. All right, so what's inside was 10x cubed. So and then you can't forget, times the derivative of what's inside. Well, the derivative of what's inside is going to give me a 30x to the second. And so when we rewrite it, it's the 10x cubed in the bottom, the derivative of 10x cubed, which was 30x squared up top. And so you do get this ratio, the derivative of the denominator and the numerator, and then a lot of times like this one we can simplify, right? This actually simplifies. You should always give your final answer simplified. The 10 divides into 30 gives me 3. I had 2 of those, 1 of those, so it means I had 1 left over. And so it does simplify to a simple number divided by x when we simplify. But to get there, you had to use the chain rule. 1 over what's inside times the derivative of what's inside, and then simplify. Alright, so the derivative of that simplifies to 3 over x. Alright, so those are the logarithmic derivative rules. Alright, again, a couple more simple examples before we get into the more complex mixed examples. So there's a couple more simple examples. So again, I have to use the chain rule when it's something inside, and the something inside could be just as simple as a number times x. So when I take the derivative of this, it's 1 over what's inside, well 1 over 30x, times the derivative of what's inside, well the derivative of what's inside 30. And it's really easy to forget that, right? If I'm going to forget something, that's what I'm going to forget. But it's important because 1 over 30x is not the derivative. If I simplify that, I would get 30 over 30x, right, the bottom and the derivatives in the top, and that actually simplifies to 1 over x. And that's always going to happen when it's a number times x inside. All right, the second example is more like the first one I did. 1 over what's inside first. So natural log of 4x to the 5th. First thing you write down is 1 over 4x to the 5th. And then multiply times the derivative of what's inside, which is 20x to the 4th. And then rewrite it. Now you could do this as a mental step and just go ahead to the second part, but I encourage you the first few times you work through this to write out that step. 1 over what's inside, because that's the rule. 1 over what's inside is the log rule, times the derivative of what's inside, which is the chain rule. All right, and then simplify. Right? A lot of these, when they're simple expressions like this, can simplify to just a number over x. And this one does. 4 goes into 25 times. 4 of those reduced with 4 of those, and so I'm left with just the 5 over an x. All right, and that's what it simplifies to. But the process, the work to get there was 1 over what's inside times the derivative of what's inside. All right, and then we simplify the expression. All right, so we'll stop there. We'll get into the more complex examples in the next video.